A helpful way of viewing an acid dissociation equilibrium is to realize that the two bases, H2O and A-, are competing for protons. If H2O is a stronger base, a stronger proton acceptor, than A-, the H2O molecules will get the protons and the solution will contain mainly H3O plus and A-. If A- is a stronger base than H2O, the A- ions will get to the protons and the solution will contain mainly HA and H2O. When beginning with equal concentration of reactants and products, the proton is always transferred to the stronger base. This means that the direction of reaction to reach equilibrium is proton transfer from stronger acid to the stronger base to give the weaker acid and the weaker base. Different acids differ in their ability to donate protons. A strong acid is one that is almost completely dissociated in water and therefore a strong electrolyte. Thus, the acid dissociation equilibrium of a strong acid lies nearly 100% to the right, and the solution contains almost entirely H3O and A- ions with only a negligible amount of undissociated HA molecules. Typical strong acids are perchloric acid, HClO4, hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, nitric acid, HNO3, and sulfuric acid, H2SO4. It follows from this definition that strong acids have very weak conjugate bases. The anions ClO4-, Cl-, Br-, I-, NO3-, and HSO4- have only a negligible tendency to combine with a proton in aqueous solution, and they therefore are therefore much weaker bases than H2O. A weak acid is one that is only partially dissociated in water and is thus a weak electrolyte. Only a small fraction of the weak acid molecules transfer a proton to water, and the solution therefore contains mainly undissociated HA molecules along with small amounts of H3O plus and a conjugate base A-. Typical weak acids are nitrous acid, HNO2, hydrofluoric acid, HF, and acetic acid, CH3CO2H. In the case of very weak acids, such as NH3, OH-, and H2, the acid has practically no tendency to transfer a proton to water, and the acid dissociation equilibrium lies essentially 100% to the left. It follows from this definition that very weak acids have strong conjugate bases. For example, the NH2-, O2-, and H- ions are essentially 100% protonated in aqueous solution and are much stronger bases than H2O. The equilibrium concentrations of HA, H3O+, and A- for strong acids, weak acids, and very weak acids are represented in Figure 14.1, and the inverse relationship between the strength of an acid and the strength of a conjugate base is illustrated in Table 14.1. Why is one acid stronger than another? Although a complete analysis of the factors that determine the strength of an acid is complex, the extent of dissociation of a binary acid, HA, is often determined by the strength and polarity of the HA bond. The strength of an HA bond, as we saw in section 8.10, is the enthalpy required to dissociate HA into an H atom and an A atom. The polarity of the HA bond increases with an increase in electronegativity of A and is related to the ease of an electron transfer from H atom to an A atom to give H plus cation and an A minus anion. In general, the weaker and more polar the HA bond, the stronger the acid. Let's look first at hydrochloric acids. Let's look first at hydrohalic acids, HF, HCl, HBr, and HI. Electrostatic potential maps show all these molecules are polar, with the halogen atom being electron-rich and the H atom being electron-poor. The variation in polarity in this series, however, is much less important than the variation in bond strength, which increases markedly from 570 kilojoules per mole for HF to 298 kilojoules per mole for HI. In general, for binary acids, the elements in the same group of the periodic table, the HA bond strength is the most important determinant of acidity. The HA bond strength generally decreases down the group because overlap between the 1s orbital of the H atom and the larger, more diffuse p orbital of an A atom decreases with increasing size of the element A, and so acid strength increases. For HA, A equals F, Cl, Br, or I, for example, the size of A increases from F to I, so bond strength decreases and acidity increases from HF to HI. Hydrofluoric acid is a weak acid, whereas HCl, HBr, and HI are strong acids. As a further example of this effect, H2S is a stronger acid than H2O. For binary acids of elements in the same row of the periodic table, changes in HA bond strength are smaller and the polarity of the HA bond is the most important determinant of acid strength. The strength of binary acids of the second row elements, for example, increase as the electronegativity of A increases. As the electrostatic potential maps show, the CH bond is relatively nonpolar, and methane has no tendency to dissociate in water into H3O plus and CH3 ions. The NH bond is more polar, but dissociation of NH3 into H3O plus and NH2 ions is still negligibly small. Water and hydrofluoric acid, however, are increasingly stronger acids. Periodic trends in the strength of binary acids are summarized in Figure 14.2. Oxyacids such as H2CO3, HNO3, H2SO4, and HClO have a general formula HNYOM. What is that? What are those? I don't know. Something. Where Y is a non-metallic atom, such as C, N, S, or Cl, and N and M are integers. The Y is always bonded to one or more hydroxyl groups and can be bonded, in addition to one or more oxygen atoms. So one or more. Okay. So this is for oxyacids. Because the dissociation of an oxyacid requires breaking of an OH bond, any factor that weakens the OH bond or increases its polarity increases the strength of the acid. Two such factors are electronegativity of Y and the oxidation number of Y in the general reaction. Let's see here. For oxyacids that contain the same number of OH groups and the same number of oxygen atoms, acid strength increases as the electronegativity of Y increases. For example, the acid strength of hypohalous acids, HOI, where Y equals Cl, Br, or I, increases as the electronegativity of the halogen increases. As the halogen becomes more electronegative, an increasing amount of electron density shifts from the OH bond towards the halogen atom, thus weakening the OH bond and increasing its polarity. As a result, the proton is more easily transferred to a solvent water molecule, and so the acid strength increases. For oxyacids that contain the same number of Y but different number of oxygen atoms, acid strength increases as the oxidation number of Y increases. The oxidation number of Y increases in turn as the number of oxygen atoms increases. This effect is illustrated by the oxyacids of chlorine. As the number of oxygen atoms in HClOm increases, an increasing amount of electron density shifts from Cl atom towards the more electronegative O atoms. The amount of positive charge in the chlorine atom therefore increases as its oxidation number increases. The increased positive charge on the chlorine atom in turn attracts an increasing amount of electron density from the OH bond, thus weakening the OH bond and increasing its polarity. As a result, the proton is more easily transferred to a solvent water molecule. Another factor that affects the acid strength of oxyacids is the relative stability of the corresponding oxyanions. The ClOm- anion becomes more stable as the number of O atoms increases in the series. Because a larger number of electronegative O atoms can better accommodate the anion's negative charge. As the stability of the anion increases, the corresponding acid has a greater tendency to dissociate. The increase in acid strength with increasing number of oxygen atoms is further illustrated by oxyacids of sulfur. H2SO4 is a stronger acid than H2SO3.